Okay, Assalamualaikum warahmatullahi wabarakatuh. Today we're going to continue with a three-phase half-wave uncontrolled rectifier, and this is the course outcome, the section outcome, which is after completing this section, the student shall be able to describe the operation of the three-phase half-wave uncontrolled rectifier, derive the quantities related to the performance of the rectifier, solve problems related to the rectifier, and finally simulate the circuit using DC. So basically, it's the general section outcome or course outcome, right? So before we proceed to the three-phase half wave uncontrolled rectifier, let's give us a quick revise or quick recap on the basic electrical concept. Okay, I would stress on the use of the notations when going to derive later on. We're going to use a symbol notations, and for the three phase, it's very crucial. It's very important that we maintain the notations as in this chapter 2.2. Okay, so the small Vt is the instantaneous voltage. Okay, this is actually the equation for any instant, right, with respect to t, the time domain, time. And then we have V phase, right? A capital V phase. This is the RMS of phase voltage. So we talk about three phase. We're going to have, we talk about in Malaysia, we have 240 volt RMS, right? And this also known as line to neutral voltage. So if you think about, we usually assume we have a Y connection. Okay, we have a Y connection. So the center point is always the neutral point, and then we're going to have VR, red phase, VB for example, and we have V yellow. Okay, so when we talk about phase voltage, it is actually the phase voltage, or you can put it also as a line to neutral, right? Line to neutral voltage. And then we also have this peak value. The peak value is actually the amplitude of your phase waveform voltage. So this will be the V will be at phase, right? And we also have the line to line voltage. So line to line voltage between line and line. So for example, here we have V yellow and V blue. And if you have the arrow from there to there, then we have V blue and V yellow. So this is line to line voltage. And we know that V line to line, we talk about RMS, this is always root 3 V phase for a Y connection system, isn't it? Okay, all right. And then what else do we have? We also have this, if I draw it in the phasor diagram, so I can have, this will be my yellow phase, this could be the, sorry, this is a red phase, yellow phase, and we have this blue phase here. And there are 120 degree phase shift. There are 120 degree space, which is other 120 degree. And if you talk about line to line, so this is the V red, V yellow, V blue. Okay, so we talk about line to line, so the V line to line. Oh no, I can do it properly. So if you talk about V red yellow, so we're going to find the V red yellow phasor diagram. So what we're going to do is V red minus V yellow, isn't it? So in terms of the phasor diagram, so this will be my V red, and then we have this is plus Vy. Now at the end of the tips of VR, you have this V yellow, which is the opposite of a Vy. Yes, so we have VR. So at the end of VR, then we have minus Vy, and that will give you the line-to-line voltage between V red and yellow. Okay, so this is V red yellow. Okay, so this is a line-to-line voltage. So again, the magnitude is root 3 of VR. So you have VR right here is root 3 VR. And if we talk about the angle, so VRY actually leads. It leads by 30 degree. You can go back and prove this, right? So your line-to-line voltage is always, it's actually lead the VR phase by 30 degree. Okay, so that's the angle between V red and V red yellow. Okay, so that's very much the about the notations, and then we also like to have this how to draw. Okay, so because you're going to draw a lot, to sketch a lot on the waveforms, so we also need to have some technique to draw the three-phase waveform. If not, you're going to get into trouble whereby if you want to try to sketch a waveform, then you might probably start with V red, and then you probably, because it's 120 degree, this is, you get confused, right? So to get the next waveform, and where is the blue waveform, isn't it? You may get into trouble to draw the three-phase waveform. So here I give you some tips how to sketch the three-phase waveform properly. So you start with drawing the x and y axis. Okay, so here you have x, draw that and draw that. Okay, two horizontal dashed lines and a set of triangles. Then what you need to do is draw these triangles. So extend a bit to the negative half cycle. Then you sketch or draw the triangle. Make sure that you have at least 4 triangles. It's just a quick draw of triangles and extend to the negative. Extend to the negative. So you must extend to the negative x. Okay, and then what you do is you need to connect the tips of the triangles. So once you have this triangle, what you need to do next is just to connect the tip of the triangles. Okay, do as well on the negative side. That, that, and that. And finally, you make it bold. Okay, using colored pen, connect and bold all phase voltages. And now you want to get a proper three-phase waveform. So how to do that? You just simply make it bold. So you just trace it again. Okay, red. Then you have yellow. You can use a proper colored pen, right, to denote the red, yellow, and blue. Now you have a nice sinusoidal three-phase voltage. Right? So that's it. And you can try to draw the three-phase. So I'll give a detail how to do it. This will be discussed. When we look into the three-phase full wave rectifier, then we need to draw the line-to-line voltage. So this is for phase voltage, and this is the tips for line-to-line voltage. So I leave it to you. Make sure that you come back to this 2.3.2 and try to draw the three-phase line-to-line voltage. Right. So now I'm going to jump to the chapter 6, some introduction. Right. So three-phase rectifiers are commonly used for high-power applications. In this chapter, two topologies for uncontrolled diode three-phase rectifiers are explained, namely the half-wave or midpoint rectifier and full-wave or full-bridge rectifier. So there will be only two topologies that we're going to discuss, which is the half-wave, or sometimes the other name is known as a midpoint rectifier, or there is another name actually, which is three-pulse rectifier. Okay, and we have another topology which is full wave or full bridge rectifier, and that also there is a name. It is also known as a six-pass rectifier. So when you are sometimes the question will test you whether you know all these terms: three-phase, half wave, full wave, full bridge, midpoint rectifier, six-pass rectifier, three-pass rectifier. Okay, so you have to know which is which. Okay, so we're going to discuss on the display the circuit of the three-phase half-wave rectifier first. So we have uncontrolled rectifier. So let's look at the circuit connection. So what we're going to do is we have three-phase supply, okay, at the front side. So we have V red, V yellow, and V blue. The each of the phase here will be connected to the anode of the phase diode. For example, we have there we have a diode red, then you have diode yellow and diode blue. So the anode will be connected to the positive terminal of each of the phase supply. Right. So the anode will be connected to the positive supply of the three-phase supply voltage, and then the anode will be common. Okay, if you look at this with circuit, this is common. They are tied together. They are tied together. They are common, right? And the output of that will be connected to the load. So we have the load here, and then it's connected to the ground, and this is actually similar to this particular ground. They are the same ground. Okay, so you can connect it together, and this is circuit, and you can have the ground there, right? Okay, so we have diode red, diode yellow, and diode blue here. Okay, let's look at what happens, how to describe the circuit operation. We always in single phase it's easy, isn't it? Because we only have one supply voltage to refer to when you want to describe the operation of the circuit. So now we have three supply voltage, and how can we decide which diodes will be on at any time? So we must follow this, some tips or some key points to understand, or some rule of thumb, okay, that you need to hold with, understand, okay, and apply to describe the circuit operation. So we have three-phase supply voltage. At any instant, the diode which each anode has the highest amount of instantaneous phase voltage will conduct. Okay, so you look at any instant, okay, any point. Then we look at which supply voltage is at its highest potential. So that will determine which diode will be on. Right? So let's do it together. So let's say we have this instant at the beginning of the operation, at the beginning of the circuit operation at 0 degree here. Can you tell me, or can you guess what is the which diode will be on during 0 degree or 0 second beginning of the time? So you go back to the supply voltage, look at the supply voltage, which is the highest potential at this particular point. Definitely it is a blue voltage, is it? Okay? So which means the blue voltage here, the diode blue will be on. Okay, will be on, and the rest will be off at 0 second here. Okay, so you're going to see that diode red, diode blue will be turned on until it reach 30 degree. So this is always the 30 degree angles is always the intersection between red and blue waveforms. It is always 30 degree. So you can prove that by using the equation, supply voltage equation. Okay, then you can find 30. This is 30 degree angle. So after this 30 degree, then what you can see is now the highest potential is actually at red phase voltage. So the diode now will be commute. The current will commute. There is a commutation of current, change of current from dB to D red. So now you're going to see that diode red on. the other two diode will be off, isn't it? Okay, so and it will continue. This diode, red diode, will continue to turn on until it reach this point. So you have 30 degrees here, and this is actually 120 degree. So each diode will conduct for 120 degree, and then you have this will be 150 degrees, right? So this point will be 150 degree. Then you have the diode yellow will turn on. So here you're going to have diode yellow will turn on for another 120 degree until this point. Then you have blue again to continue until the next cycle. Okay, so this is 100, 30, so it will be 100. This is 90 degree. Okay, 90 degree, and it continue 30 degrees. So that will be 100. Okay, so this is 90 degree because you have a remaining 30 degree here. So this is also alright. So if I can again, I can mark this will be the red, the yellow, and this is the blue here, and this is also the. So that is the labeling and also the range of diode operation with respect to the supply voltage. Okay, so you have to understand this, right? So now we connect to the resistive load. So this is the you have to. I mean, if you understand, then you don't have to have a problem in memorize, in reproduce the labeling, the degree, the duration of each diode, and so on and so forth. All right. Okay. So now, okay. So what happens to the output voltage when this diode is on? So we measure the output voltage is across the load, isn't it? So this is your load. So the point is always that to the particular ground. So this is your output, the out, or sometimes we know as VDC. So the output voltage is actually measured from this point to the ground, right? So therefore, when we start at the 0 seconds, diode blue is on, isn't it? Okay, so when this is on, the rest, the other two diode is off. So which means this point will be connected to blue waveform, isn't it? So output voltage will actually follow the blue waveform. So in the circuit here, and this waveform here, so you're going to see that the output voltage will follow the blue waveforms until this point, and then it will follow the red waveform, isn't it? So we know that the red waveform will be the red diode will be turned on after this 30 degree. So now it will follow the red voltage. So I change to blue. Okay. So now it will follow the red voltage until 150 degree. It will follow the yellow waveform. This we will talk about the output voltage, and then finally it will follow again the blue waveform. So this is your output voltage. Okay, so this is your output voltage. It will actually copy the envelope. I'm going to say that it will copy the envelope of the supply voltage. So this is the envelope of the supply voltage. So here, this is your actually the output voltage. So if you look carefully, it is actually consists of how many pulses? 1, 2, 3 actually, plus with this one 3. So in one cycle there are 3 pulses. Okay? So therefore, that's why the midpoint converter here is also known as a 3-pulse rectifier, because the output voltage consists of 3 pulse of waveform. Okay, I hope you understand that. Right, so now we're going to continue on deriving the output voltage. So let's we know that the duration of the pulse is 120 degree. So in 360 degree there are 3 pulses. So each pulses actually consists of the duration is 120 degree. Okay, So therefore, if we derive for the average, we're going to divide by 2 pi over 3, isn't it? Okay, in one cycle, we're going to divide by 2 pi over 3. Okay, so to look into the output voltage, it is enough for us to look into one pulses only. So we're going to take one pulse only, and then we're going to do the integration. So we're going to take this pulse, okay, and it is actually convenient, or is very easy. I mean, it's easier for us to relocate the peak of the waveform here to 0 degree. So what we're going to do is we're going to we're going to change now from, this is at actually at, so we have 30 degree, it's pi over 2, isn't it? So now it is pi over 2, the peak is actually at 90 degree. So we're going to change that to 0 degree here, and therefore your voltage waveform will be, the peak of the voltage waveform will be exactly as 0 degree or 0 seconds. Okay, so we know that this is 120 degree. Okay, so now it is split into minus pi over 3, which is 60 degree, and plus pi over 3. So that we have the total of 2 pi over 3, which is the 120 degree. So we just consider this waveform. Now we're going to integrate to get the area under the curve, and then we're going to divide by 2 pi over 3. So this is what we're going to do. VDC equals to 1 over 2 pi over 3, right? We divide by 120 degree, and then the integrations now become from minus pi over 3 to plus pi over 3. So with respect to this waveform, isn't it? So you integrate from minus pi over 3 to pi over 3, and when you change, when you switch or change the waveform here, this is sine waveform, isn't it? This is sine waveform because it follows the yellow waveform here. So it is sine omega t, isn't it? Okay, but now as we change it to, or we shift it as so that we have 0 degree here, now the waveform here, the equation is no longer sine. Now it changed to cos theta, isn't it? So because we know that the cos waveform always do this, isn't it? So this, sorry, it has to be big, isn't it? So this is also cos omega t waveform, right? So once, because of we change the 0 degree here, the center of the peak is at 0. Now it becomes v peak cos v peak phase cos omega t. Okay, so that's why in this derivation we have the integration of minus pi over 3 to pi over 3 VDC theta, and this is output voltage, and therefore the equation now becomes v peak phase cos theta d theta. You divide 2 pi over 3 because you want to get the average, and now the final equation is VDC, the output voltage, equals to 3 over 2 pi v peak line to line. Alright, I hope it's clear now. Okay, it's 3 over 2 pi v peak line to line. Okay, or you can maintain this equation if you don't like the you want to use the peak voltage, then you can maintain this up to here. So it's the 3 multiplied by root 3 v peak phase over 2 pi, or if you want to, you know, uh, in terms of v peak line to line, then it becomes only 3 over 2 pi v peak line to line, right? So that gives you the output voltage equation, the average of the output voltage equation. And what about the output current? Again, this is resistor, so I simply V over R, V over R. So the output voltage will follow the output voltage waveform, but it's scaled down by a factor of R. So if you look at the current, so this is current 1, I1, the current through diode 1, This is current diode 2, which is I3 here. Sorry, yellow waveform, yellow phase, and then we have I3 correspond to diode yellow blue. Okay, so this is current, and the output current will actually copy the same output voltage waveform but scale down, V over R, scale down by the factor of R. Okay, so that's very much the three-phase half wave uncontrolled rectifier. And then we look into the resistive and inductive load. So if you change, okay, you remove and replace the R with, now we put the R plus L. What is the significant difference is actually if you look at into the output current. So the output current now become continuous. Okay, now it become continuous. So if you look at the front, the red phase current, it will still have this current, but then the output, I mean the top, the peak of the current now carries the supply at the output voltage, output current. Okay, so it's less ripple compared to the uh, red resistant, okay? Resistive load. Okay, that's the only difference. But if you look into the output voltage, is very much similar to the resistive load. Okay, for resistive and inductive load. And therefore, if you normally we're going to replace that with a constant current, isn't it? And we have this problem, and then we're going to remove R plus L, and we're going to remove that, and we normally put a constant current. So what happens if you have a constant current? This will become flat, isn't it? So that become flat. Okay, the current become flat. Right. Okay, so next we're going to look into the 6.2.3, which is the effect of line or source inductance on current commutation for three-phase half-wave uncontrolled rectifier. So this is again in practical. There's always a source inductance, supply inductance. How this get into the system is actually from the transformer winding. It could be from the cabling. Okay, so that actually introduce or add the additional line or source inductance in the system. This is the front side, close to the supply voltage. Okay, so we're going to look at the effect of having this source inductance to the three-phase half-wave uncontrolled rectifier. Okay, so to be able to explain these conditions, we're going to consider the transfer of current from, okay, we have this is red phase voltage, right? So this is DR, this is during DR red diodes on, and then we're going to look at the transfer of current from red diode to yellow diode. Okay, so we know that this is 30 degree. Okay, and the duration of the pulse is always 120 degree. So here you have 150 degree with respect to 0 degree from the supply voltage here. So this is 150 degree. So we're going to focus on this particular point where we see that the yellow phase current phase voltage is higher than the yellow the red phase voltage. Okay, so you can read this, right? And then we're going to consider actually in doing the analysis, we're going to have three sub analysis. We're going to consider we're going to analyze three category, three item. The first one is that we're going to look at the instantaneous, or look at this waveform. Okay, so during the overlap, so we know that this is overlap current. During this overlap, the voltage is no longer follow the yellow voltage, but now there is a loss. There is a loss here, isn't it? There is a voltage drop or voltage loss here. So it actually follow, if we look closely, it's actually divide the waveform into two apart, isn't it? It's, it is average between the two waveform here. It run in the middle between the two waveforms. So we're going to look at what will be the instantaneous output voltage equation during this overlap. And number two is we're going to look at the overlapping angle, the U. What is the equation to describe the overlap angle or the interval? Sometimes we call it a commutation interval. Commutation interval or overlap angle. Sorry for the writing. Okay, commutation angle or commutation interval or overlap angle. And then finally, we're going to look at how to get the equation for the average output voltage. Okay, so this is circuit again. This is our main circuit. We add this source inductance before the diode, and then this is will be replaced. Okay, we're going to remove that and replace with a constant current with IDC equals to IDC with a certain amount of IDC, and the output current is ripple free, is a constant current. Okay, so if you look at this point, right? So as the yellow now become the highest voltage compared to the red phase, now we can see that the red current start to decay, start to fall with a certain rate, and at the same time we're going to see that the red, this should be yellow, this should be red. Okay, sorry, can you change this? This should be yellow levels here, IDY. Okay, this should be IY here, right? So the IY will increase. Okay, the red, yellow, red phase reduce at certain rate, and we're going to see that yellow increase at a certain rate until it reach the IDC, the output current. Okay, so during this time, we're going to see that the diode R and diode yellow are turning on during this overlap angle. Is it? Okay, because both are carrying current here. So during this time, we're going to see that the voltage is at the middle and run in the middle between V red and V yellow. Okay. So now we're going to look at what will be the equation for output voltage. Okay, so to do that, we're going to draw the equivalent circuit during overlap. So just consider between red, yellow voltage, and we have this diode DR on, so it will appear as a short circuit. So this is DR, and then we also have D yellow bottom here. Okay, and this is your constant current, and this is go back to your neutral point here. So we're going to have IR plus IY equals to IDC. Right. So at any instant, the current IR plus current IY equals to IDC, and then we have this DI over the T, I mean the source inductance for both phase, red phase and yellow phase. Okay, now we're going to apply the KVL across the, the outer, let me see, VDC, VR. Okay, so you just follow the, from the phase, red phase voltage path. So we're going to consider this. So here, the KVL, through that, and come back to this point. Okay, so that we give this equation. Isn't it? So you have minus VR, and then plus LS DIR over DT to get the voltage across LS here, and then you have V out, isn't it? Plus V out equals to 0, or VDC, or V out. Okay? So that form the first equation here. VDCT equals to VRT minus LS DR over DT. And then next is to use this loop. Start from there, go to that loop, go to that loop, come back to that. Yeah. So we have minus Vy plus Ls diy over dt plus Vout or Vdct equals to 0. So this is also Vdct, the output voltage. Okay. So you have second equation from this loop. Alright, so you have this both equation, and then adding both equations. So you add both equations, then you get 2 VDC equals to VR plus Vy minus Ns di over 2. However, by KCL, okay, from this KCL, Kirchhoff current law at this node, this point, IR plus IY equals to IDC, and therefore, from the sum rule of differentiations, we know that there is a rule of sum rule for differentiations, whereby the individual derivation dir over dt plus diy also equals to d. You sum the component first and then you differentiate. Okay, that also will give you the same results, and therefore dir plus diy equals to idc. So a constant, when you derive a constant, you will get the 0, isn't it? So, and therefore this equation equals to 0. Okay, all this equation equals to 0, and therefore what left is only vdct equals to vr plus vy t over 2. So that's why if you look at the waveform now, VDC is actually in the middle between the two waveforms. It's the average between the two waveform VR and VY. Okay, so that is proven by this equation, instantaneous equation here. Sorry, equation 6.7. Okay, so next we're going to continue with overlapping angle or commutation interval U. So we consider the similar equation, equivalent circuit as figure 6.4, but now um, we're going to add the U. We're going to add additional current IU in the circuit, and the direction of the IU should follow the direction of current which flows after the overlapping period. We know that after the overlapping period, yellow phase current will flow, and therefore you need to assign a current that follow the yellow current. So here in this circuit, you're going to have this direction 3, because yellow will flow, yellow current will flow after the overlap. Right? Okay, so now you again apply KVL. So you have minus Vy plus Vr plus 2Ls diu over dt, and now we have Vy equals divided by minus Vr equals to 2Ls diu over dt, and then it's convenient to convert that into radian, and now it become Vyr. Okay? This is a line to line voltage now. So this becomes line-to-line voltage. 2Ls diu over dt, convert to radian, then there is a omega appear here. I think we have done this before. Okay, diu over d theta, and then you integrate both side equation, and with the time origin assumed to be at beginning of current, so you have 0 to u. So you follow this. Okay, so the limit will be from 0 to u, but for the current, we start from 0 to IDC. Great. So the limit is 0 to IDC. Okay. So your now it become, if you look at the limit again, it become that. Sorry. Okay. So this is the limit. Based on the current waveform just now. Okay. And then you integrate, solve that, and finally you find out that the U, the overlap angle, equals to inverse cos 1 minus 2 omega s I dc over V peak line to line. So now you have the V peak line to line notations appear in your equations here. Okay, so that will mean U. Next is to look into the average output voltage DC. So similar strategy, we know that this is the average voltage drop. So if you can find the average voltage drop here, so just simply minus, because we know that the equation for the 3 pulse without the source inductance, the average equation for the output voltage without the source inductance, and then we're going to subtract with this average of the voltage drop. Okay, so we just need to evaluate for this small area here. So you can do this by get this equation. So the V drop equals to, we know that this is Vy, isn't it? So this is your Vy equation minus, right? So you have to minus this waveform, isn't it? Okay, to get the missing area. Okay, because when we integrate, we're going to have to get the area under the curve, isn't it? So if you integrate Vy, you will get the whole area under the curve there. And then if you integrate this, you will actually obtain this only area here. So if you subtract, then you get this missing area. Okay, so that's why you have Vy theta minus Vr plus Vy theta divided by 2. And do it again, you have Vyr. And if you look closely, equation 6.11 actually equals to equation 6.9. Okay, you can refer to your note again, equals to equation 6.9, and therefore we just use whatever the result that you obtained just now. And then we know that the V drop, the V drop equals to omega LSIDC. I think there is a slight it's a different from your a draft, isn't it? And I did mention, I did send you the message that you need to correct this 6.12, right? So this is V drop. If I'm not mistaken, I put an area. So remove that area, put a V drop, voltage drop, and that gives you omega LSIDC. And because we want to look at the average of the voltage drop, so you have to divide by 2 pi over 3. Each pulse is 2 pi over 3, so you divide that, you get this. And therefore, you just simply, this is from your equation before, without the source inductance. Without the source inductance, okay, you get this equation. Therefore you minus with the voltage drop, and that will give you the average output voltage equation. Okay, and you can try this. Just quickly look at the problem 1. Given for the 3-phase half-wave uncontrolled rectifier, Vs equals to 240 volt, constant load IDC 20 amp, line inductance Ls 5 mA. So you need to actually be careful. So what are given here is that this is it line to line voltage or phase voltage? This is RMS phase voltage, isn't it? 240 volt. Constant load current IDC, this is I0 IDC 20 amp. Line inductance 5 millihenry. Sometimes you are given in terms of XLS. Okay, for example, LS 10 ohm. Okay, so you have to be careful. This is reactance. Okay, this is reactance. This is inductance. So you have to modify the equation here, isn't it? You have to modify the equation there. Okay, that is problem 1. Okay, so I think that's it for the 3-phase half-wave uncontrolled rectifier. Okay, so you have to go through again, line by line, look at the equation, right? So you have to understand that you cannot simply listen and then you assume to understand. You have to look at the equation again and again and try to do it from scratch, right? Not to memorize everything. You start with a blank paper. Okay, start with a blank white paper. Start to sketch the circuit, draw the circuit, and then the waveforms, and then that particular waveform you solve for your whatever you have, the output voltage equations and the rest. So you have to do it systematically, and that's why this is known as a discipline. Discipline, ilmu, discipline ilmu. We talk a lot about discipline ilmu. So this is you have to be disciplined to get the ilmu, right? Okay. Assalamualaikum warahmatullahi wabarakatuh.